Welcome back, ladies and gentlemen, to another video with Mr. Kenton for AP Chemistry. And I'm excited to be here with you guys today because we're going to be taking a look at our newest unit, which is going to be taking a look at intermolecular forces and properties. Now, as we're moving forward, we're going to be looking at how intermolecular forces apply to solids, liquids, and gases, and also how that plays out in solutions. And so it's going to be building on and looking at interactions, not just in between atoms, but looking at how do molecules interact with each other at the particle level. So I hope you guys are ready. It's a pretty interesting topic. And so for those of you who don't remember gases or anything like that, don't worry. We're going to get you covered here, so don't stress out. But hope you're ready to join along for the ride. Let's hop to it. All right, so the first thing that we're going to take a look at are intermolecular forces, and you can find this material in Chapter 11 of the Brown and LeMay textbook. This is coming specifically from Section 2, and here are the problems that you're going to need to complete as it pertains to Chapter 11. So when you finish up watching the videos as we finish up this particular section, go ahead and go back and start working on those videos. Now, let's take a look at these intermolecular forces. Now, if you think about the unit we just finished up when we were looking at bonding, we weren't looking at intermolecular forces, we were looking at intramolecular forces or intraparticle forces, right? So those would be the interactions between individual atoms to form bonds. Well, intermolecular forces are going to be these interactions between two or more molecules or two or more compounds and how they interact at the particle level. Now, so here's our definition for our intermolecular forces. The forces that hold solids and liquids together are called intermolecular forces. Now, to put this in perspective, our intermolecular forces are much weaker than ionic or covalent bonds. And the reason for that is because we're no longer talking about interactions between individual nuclei of the atoms and how bonds are being formed. We're simply looking at how are the particles, the molecule itself, interacting with another molecule. And so it leads us to significantly weaker interactions than our intraparticle forces. So just kind of keep that in the back of your mind when you start thinking about the strength of these things. Certainly our ionic and covalent bonds are stronger than the intermolecular forces that we're going to be looking at in this particular unit. Now, for example, to put this in perspective, when you think about the energy that's required to convert hydrochloric acid or hydrogen chloride from a liquid to a gas, notice here it's listed as 16 kilojoules per mole. Now, I mean, that's a decent number, but when we compare that to the actual energy required to break the bond between hydrogen and chlorine in this particular molecule, it's going to fall very low, right? So HCl, to break it into its individual elements, is 431 kilojoules per mole. That is significantly greater than the energy required to vaporize it, to take it from a liquid to a gas. So that's just one way we can get an idea of how these intermolecular forces are weaker than our intraparticle forces. Now, when we talk about a substance melting or boiling, it's important to recognize that what's changing within the substance is the intermolecular forces are being broken, not the covalent bonds. And so let's take a chance to look at what are the different types of intermolecular forces that we're going to look at that we can interact with within the context of this topic. Now, as we look at intermolecular forces, an important thing to recognize is that intermolecular forces play a biggest role in physical properties of our substances. And so things like melting point and boiling point are going to tell us something about the intermolecular forces and the strength of those forces within our molecule, right? And so boiling point is going to be a reflection of intermolecular forces. So if we have a high boiling point, then what that's going to do for us, it's going to indicate that it has strong attractive forces or strong intermolecular forces. Additionally, if we look at something that has a high melting point, that's also going to reflect or give us some insight as to the attractive forces that are keeping that particular substance together. Now, when we start to take a look at our intermolecular forces, they're going to fall into one of four categories. So our first one are what are called ion-dipole forces. The second are dipole-dipole forces. The third are London dispersion forces. And the fourth that we're going to take a look at is called hydrogen bonding. And it's important to recognize that hydrogen bonding is simply a special type of dipole-dipole interaction. It's a special type of dipole-dipole force. Now, as we move forward, we're going to look at each of these types of intermolecular forces more in depth. So just kind of know that as we go forward. All right, so let's take a look at first our ion-dipole forces. Now, ion-dipole forces are exactly what they sound like. It's an interaction between an ion and a molecule that has a dipole, okay? So if you think about that, the implication there is that in order to have ion-dipole forces, you have to have an ionic compound that is interacting with a polar molecule. Now, in most instances, those interactions are going to take place in solution. So you're going to have your ionic substance that's been dissolved in water, and it's interacting with some sort of polar solvent, in most cases, water for our purposes, right? Now, when you start to take a look at the intermolecular forces, ion-dipole interactions are the strongest of all the intermolecular forces of attraction. And it simply has to do with the fact that of the differences in the charges and how they interact within the ion and the dipole that cause it to be extremely strong interactions. Now, a good example of this would be something like sodium and chloride that are being dissolved in water. And so if you take a look at this image that's over here to the right, what you can notice is you've got a cation, which is in the middle, and you've got your anion, which is in the middle as well. But you notice, so the purple sphere, that's going to be sodium. So on the left, this would represent the Na plus ion. And over here on the right, this is going to represent the Cl minus ion. Now, what you notice by looking at this particle level representation is you should notice that around the sodium ion, that all of the negative ends of the water molecule have oriented themselves so that they can interact with the cation, the Na+. And if you take a look at the chloride ion, you should notice that the water molecules have flipped. The positive end of the dipole, which in this case would be the hydrogens, are surrounding themselves around that chloride ion so that they can interact and form this ion-dipole force. That's how we would represent that at a particle level. Now, our next type of intermolecular force are our dipole-dipole forces. Now, you might hear me refer to them as dip-dip interactions. I do that because that's what my chemistry teacher said to me. If that bothers you, I'm sorry. I'm just going to sometimes refer to it as dip-dip. It sounds kind of funny, but it's something that kind of stuck with me, and so I'm passing it along to you guys as well. So our dip-dip interactions are going to take place when we have two polar molecules that are interacting with each other in their solid or their liquid state. So these are going to exist between neutral polar molecules. And so if you take a look at the image that's just populated up on the right, again, you've got this interaction where you have the negative and positive end of your molecule. Notice how the adjacent molecule has oriented itself so that the positive and negative ends can interact with each other. And so when you start to look at things at the particle level, we look at solids and liquids and we see that molecules that exhibit dipole-dipole interactions, their particle level diagrams are going to show something like that. Now, dipole-dipole interactions are going to be weaker than our ion-dipole forces. And it simply has to do with the fact that there is no specific substance that has an overall charge. And so it weakens that interaction between the two substances. Now, as we begin to look at dipole-dipole interactions, certainly we might have to make a comparison between which substances have a greater dipole-dipole interaction. And so something that we can consider is that if you're looking at two molecules that have about the same mass and size, then what we're going to find is that the dipole-dipole interactions are going to increase the more polar the molecule is. And so if you take a look down at the bottom, you see that table that's been listed here. It gives a list of molecules, and all of them have roughly the same molecular weight. We're between 40 and 50 AMU. And as you can see, as we increase the dipole moment, so you look at propane, certainly not a very polar molecule, has a boiling point of 231. But as we keep moving down, we see that as the dipole moment increases, we get an increase in that boiling point. So it's indicating that the dipole-dipole interactions would be strongest in acetonitrile in this particular diagram. I hope that makes sense. Now, the third type of intermolecular force that we need to talk about are London dispersion forces. Now, London dispersion forces, you can think of them as instantaneous dipoles that are being formed within your molecules. And let's just talk about how do those instantaneous dipoles form. So London dispersion forces, this is the weakest of all the intermolecular forces. And so what we need to recognize is that London dispersion forces exist between all molecules. And it's also important for me to mention at this point, ladies and gentlemen, that it's possible for a molecule to contain multiple types of intermolecular forces. So for example, when we talked about on the previous slide something that had dipole-dipole interactions, its strongest intermolecular force will certainly be those dipole-dipole interactions. But it's also going to contain London dispersion forces as well. So it's just something that I want you guys to consider moving forward. Just because something has is listed as having dipole-dipole interactions, it also has London dispersion forces. Now, please keep in mind, if something is nonpolar, it's only going to contain London dispersion forces. Now, how do these London dispersion forces form between our molecules? So what happens is, like, if you take a look at this diagram at the bottom, you've got two helium atoms. Well, so what happens is one molecule's electron cloud is going to become distorted because the atoms, the electrons within their electron clouds, are interacting with each other. And so when negative charges get close to each other, we know that they repel. And so what this does is it creates an instantaneous dipole within that one particular atom or molecule. And then what that molecule is going to do is create other instantaneous dipoles in an adjacent molecule or atom. And so if you look down at this diagram here at the bottom, as you can see, you've got your two helium atoms that are interacting, and the electrons in this helium atom are over here currently on the left, and over here they're not really evenly distributed. So what's going to happen is the nucleus from this helium atom over here is going to experience an attraction to the electron cloud of the other helium. Well, what that's going to do is it's going to cause the electrons in helium atom number 1 to shift further to the left, creating this distortion on its electron cloud, and then it's going to momentarily create an interaction between those two atoms. And so that's how London dispersion forces form within a given molecule. And again, these are instantaneous dipoles, and they're not necessarily permanent like the dipole that can be found in a polar molecule. I hope that makes sense to you guys. Now, again, these forces between these instantaneous dipoles are called London dispersion forces. Now, some more information on our London dispersion forces. London dispersion forces are going to depend on the shape of the molecule. And so certainly what we're going to find is that certain shapes tend to lead to increases in the London dispersion forces that molecules exert on each other. One thing that we want to consider is that if we have a molecule that has a very large surface area, what's going to happen is that means that those molecules have more opportunities to come in contact with each other, which means they're going to experience greater dispersion forces overall. And so if you take a look here at the image that's going to show up over here, we can start to see that. So London dispersion forces between spherical nonpolar molecules are lower than the forces between long nonpolar molecules. And so if you take a look, you've got pentane and neopentane. So N-pentane would just simply be this long carbon chain of pentane, whereas neopentane is kind of the structure where it's kind of balled itself up. So if you look at the boiling points and we compare pentane to neopentane, the boiling point of the long chain pentane is 309.4 Kelvin. But when you look at neopentane, it's at 282.7. And so what that's communicating to us is because that pentane has that larger surface area, there are more opportunities for the pentane molecules to interact with each other, which is simply not possible in the neopentane molecules that you see there. So that's what's going to account for that difference in boiling point, because the London dispersion forces are weaker. Right? So less surface area, less force. The second thing that you should consider is that the larger the molecule is, and something that we want to consider here when we say large molecule, greater number of electrons within the molecule. The more polarizable it is for that molecule, the more polarizable the molecule is, so the stronger its intermolecular, the London dispersion forces. Now, polarizable simply means that it's easier to create instantaneous dipoles within your molecule, right? I've heard it kind of described it means your molecule is more squishy, right? It can be more easily distorted in terms of its electron clouds, and therefore it's going to increase the London dispersion forces experienced by that molecule, right? And so when you start to look at this table, we can see that play itself out. Another thing to consider is that London dispersion forces increase as molecular weight increases. That's getting at that polarizability. So you've got F2, Cl2, Br2, and I2. You see their weights, they're going up, but you also see that their boiling points are going up. Now, again, don't just simply use the weight component. Make sure you're taking a look at the number of electrons, right? So we could definitely identify I2 has way more electrons than F2, which is what's accounting for that larger boiling point. And we see the same thing happening with our noble gases. Helium is our lightest noble gas. It has the lowest boiling point. Xenon is our heaviest noble gas. It has the greatest boiling point. So that would indicate that xenon has stronger London dispersion forces than helium does. All right, now our last type of intermolecular force that we need to consider is a special case of dipole-dipole interactions, which is called hydrogen bonding. Now we need to be careful here when we start talking about the name hydrogen bonding, because this is not the same thing as like a bond that forms between two atoms. This is not like ionic, covalent, or metallic bonding. This is, again, it's a type of intermolecular force of attraction between individual molecules. Now, it's a special case of dipole-dipole forces. And the reason why it's special is because it only is found in specific types of molecules. And those are molecules that contain HF bonds, HO bonds, or HN bonds. And so what we've determined is that experimentally, when you look at the boiling points of compounds that have these types of bonds in them, their boiling points tend to be abnormally high for what we would anticipate. And so what chemists were able to deduce is, okay, the intermolecular forces within these molecules that have these types of bonds are abnormally strong. And so in order for a molecule to have hydrogen bonding, it has to meet a couple of criteria in order for that to happen, right? So obviously, because it's a type of dipole-dipole interaction, it goes without saying it has to be a polar molecule. The second thing you need to consider is that hydrogen has to be bonded to a small, highly electronegative element. For our purposes, those are going to be compounds that H is going to be bonded to F, O, or N. Okay, so if hydrogen is bonded to an F, O, or N, then there's a possibility that there could be hydrogen bonding. The next thing that we want to consider is that there needs to be an unshared electron pair on a nearby small, highly electronegative ion or atom. Usually in this case, we're talking about fluorine, oxygen, or nitrogen on another molecule. If both of those criteria are met, then hydrogen bonding can form between those molecules, right? So you've got hydrogen bonded to either an F, O, or N, and then there needs to be an unshared electron pair on an F, O, or N on an adjacent molecule that can interact with this other molecule. And hopefully on the next slide, when you get to look at kind of some examples, that'll be a little bit clearer. All right, so here are our examples. And so you got 1, 2, and 3. So notice what we're showing in number 1 when you're looking at the water molecules as they're interacting. Notice that the hydrogen from one water molecule is interacting with the lone pairs on the oxygen of the other water molecule. Okay, we can see that within ammonia as well. We see the hydrogen from one ammonia forming an interaction with the lone pairs of a nitrogen of another ammonia molecule. And I like example number 3 because it reminds us that hydrogen bonding doesn't necessarily have to be between two of the same molecules. So here we have the hydrogen on an ammonia molecule that's interacting with the lone pairs of the oxygen on a water molecule. All right. Now, from that experimental perspective, here's what we were talking about with having extremely high or abnormally high boiling points. So when you start to look at, for example, water, for example, water has a temperature which is a gas at 100 degrees Celsius, right? Because that's when it boils. Now, when you look at other compounds that correspond to, that are in that same group as oxygen, like H2S, H2Se, and H2Te, notice that there is a very big difference. I mean, we've got temperatures where it's converting into a gas that's less than 0 degrees Celsius. And so the reason for that is because of the hydrogen bonding that's within a water molecule. Excuse me. Now, if you notice in black what we're showing here, you've got CH4 that doesn't contain any polar bonds or any dipole-dipole interactions, so it has a much lower boiling temperature. The same thing is true here for other substances. We're seeing very different interactions, and that's what's causing the low boiling points. Now again, those that are listed on with the black curve, those are nonpolar molecules. With the red, those are polar molecules. Water's just abnormally high because it contains hydrogen bonding. And so because of that abnormally high boiling point, we know that it exhibits hydrogen bonding. All right, ladies and gentlemen, that's going to conclude this particular video as we've introduced intermolecular forces. I hope that this was helpful to you. Remember, if you need to look at something else, go take a look at this video again. If you have questions, feel free to ask them during class, or if you have a specific question, come to office hours. But guys, I really appreciate you guys taking the time to watch this. I hope it was insightful, and look forward to seeing you guys again real soon. Take care.